In this problem on photoelectric effect, it is given that when a radiation of wavelength lambda hits a metal surface, the stopping potential of the ejected photoelectrons is 4.8 volts. If you change the radiation to a different one with wavelength doubled, the stopping potential becomes 1.6 volts. We're asked to find the threshold wavelength of the metal. We all know that each metal has something known as a work function associated with it. Now, what is this work function? Work function is the minimum energy of the photon that is capable of ejecting a electron out of the metal. Okay, so this is the minimum energy required. Okay, so with this energy, the electron just comes out of the metal surface. It will not have any kinetic energy with it. Okay, so minimum energy required, or you can say minimum energy photon. So which we can write it as h into frequency minimum. If frequency is minimum, then the wavelength of the photon is maximum, right? So hc by lambda max. So this lambda max is what we need to find here. So now let us take a look at the photoelectric effect experiment setup. So we have here a metal. Okay, the light hits that metal and the energy of the photon is picked up by these electrons. Okay, and then each electron when it comes out of the metal surface, if the metal is hit by photons having sufficient energy. Okay, so that is why we have this requirement of minimum frequency. Now the photo electrons that come out of the metal surface, they come out with varying velocities, hence they come out with varying kinetic energies. Now usually the metal which is opposite to this metal on the left hand side is kept at a positive potential, so that the electrons are motivated to move towards that plate. But here when we try to get the stopping potential, we are trying to stop the electrons from reaching the opposite plate. So if you look at the battery, the negative terminal of the battery is connected to the opposite plate. So what would happen when you do this? So this plate has negative potential and the plate which is hit by the photons has positive potential. So the electric field goes from left to right. And we know electrons cannot move in the direction of the electric field. So hence they will lose energy. Okay. And if we simply apply work energy theorem, if we are keeping a potential which is just sufficient to stop even the photoelectron having maximum kinetic energy, such a potential is known as the stopping potential. So let's assume an electron comes out of the metal with maximum kinetic energy, which is K max, and then this energy vanishes. Okay, so it becomes zero. So what is the work done by the electric field? It is charge multiplied by the potential difference, so which is E into V naught. Okay, now let us use this in the photoelectric effect equation, which is something like this, right? So H into F, which is the energy of the photon. Some of this energy is utilized by the electron to overcome the collisions inside the metal. So that is why we have that work function, minimum energy requirement, plus K max. Okay, so since we are trying to find the threshold wavelength, let's write everything in terms of wavelength. So the left hand side we have hc by lambda, and work function is hc by lambda max. Maximum kinetic energy is E into V naught. Okay, so in the first case, when the wavelength is lambda, the stopping potential is 4.8. Okay, now when you double the wavelength, the energy of the photons will be hc by 2 lambda. Okay, so the energy of the photons will go down, and this again should be equal to the work function, which is hc by lambda max, plus because the energy has come down, the stopping potential has to reduce, right? Okay, so the kinetic energy will not be that great now. So E into 1.6. Okay, now we need to find lambda max in terms of lambda. So what can we do here? So if you look at the right hand side, we have 4.8 and 1.6 in the second equation. So we can just subtract the first equation from 3 times the second equation. Okay, so multiplied by -3, the second equation is multiplied by -3, and then we can, I think we can add. Okay, so if I'm multiplying second equation -3, we can just simply add. So when I add the left hand sides, what do I get? I get hc by lambda plus minus, not plus, minus 3 times hc by 2 lambda, and the right hand side I have hc by lambda max minus 3 times hc by lambda max. Okay, so E and the stopping potential, they disappear. Okay, so what do we have on the left hand side? We have 1 minus 3 by 2. On the right hand side I have 1 minus 3. So throughout hc is common. Okay, it is present everywhere, so you can ignore that. And then the left hand side I can write it as 1 minus 3 by 2 is minus half, and we have 1 by lambda. The right hand side I have 1 minus 3, so that is minus 2 by lambda max. So from here lambda max will be 2 into 2, so that is 4 lambda. Okay, so the threshold wavelength of this metal is 4 lambda.